Hey, Aaron, and article too. I'll be back in just 1 minute. I'm gonna get some water.
Oh, there's supposed to be a chat window as well. Probably for like questions. I don't know how this works.
There should be a chat window button up in the top left, at least there is for me.
Mm. Hello, all. Can any of you hear me? Okay, good. So I do not know, since most of you have your videos on mute, I will be making awkward eye contact with anyone who chooses to keep their video on. Of course, you won't know that. Thanks you all for coming to our special at-home session of computer science. I'm sorry I couldn't be there today, but when I realized at 3 a.m. that I wasn't going to fall asleep, I'm like, I don't think it's safe for me to be on the roads. So we will get an extra punchy session of computer science today. So let's see. So I'm going to try and put the screencast on and share the slides. And hopefully you all are seeing that now. Oh, and apparently now my dog wants to come in here. Fun times. All right. Where we last left off, we were talking about. Okay, can everyone see the slides? Okay. Thanks, Kelly. So, Kelly, do you need me to hold on for a second while you're trying to figure this out? Okay, so who's in the classroom right now, just out of curiosity? For those who are wondering, the chat window, apparently Kelly has said that about half the class is in the classroom trying to get the whole thing set up. So, okay, cool. Awesome. So you guys can see me? Well, thanks for coming to class. You could have this in your bedroom, but I appreciate that you came to the classroom. Cool. So yeah, so for those who joined in late, thanks for coming. Sorry I couldn't be there today. And since naturally I have no video of the classroom, I assume everyone's paying full attention to everything I'm saying. What we're going to talk about now is, and before I go on, can everyone see the slides? Okay, cool. Awesome. So what we're going to talk about today is we're going to talk more about the different types of, we're going to go through Peterson's solution a little bit more and talk about the problems we ran into earlier. So the Peterson solution, what we talked about earlier is that Peterson's solution was a way that we could protect threads from entering the critical section at the same time. And so we worked through the scenario where we had essentially two different two different threads going at exactly the same time, we had thread 1 entered into the critical section, and when it entered into the critical section, what ended up happening? How am I going to do this on here without drawing? Can I do something? Will this work? Sorry, I'm trying to figure out what's going to be the best way to do this so that y'all can see it, because I really need to draw on here. So why don't I keep a running tab of what's going on? So I'm actually going to let's change to a different. untitled text. Okay. So, sorry, I had several students email me panic messages all at the same time. A lot of people telling me they're sick today, so I guess a lot of people got sick. Okay. So we're going to have, and let me increase the font size so you all can see this. There you go. So we're going to have two threads both running at the same time. So this is the code that they're going to run. This code, everything up here is run beforehand, and everything down here is run at each thread individually. So we're going to create these and mark them as, show you what the code looks like if we were to just say process is going to be thread 0, which means other is going to equal to 1. And then here, interested process is going to be 0, turn 0, process 0, interested 1, process 0, process 0. That's one code. And the other one is the other one is going to be process 1, other is 0, process 1, process 1, turn 1, interested 0, process 1, process 1. So what'll happen is when you want to enter the critical section, you'll first call the enter region, and then you'll do whatever you want to do in the critical section, and then eventually you'll leave it. All synchronization methods have this general approach where there's a period of code that both things run beforehand. In this case, it's establishing the turn array, establishing the turn variable, and establishing the interested array. So what's interesting is that these things can be interleaved however we want to. And so what can happen is we could have, in effect, these two, and I'm just going to tab over so we can sort of see what would happen if we were to interleave. We can have them interleave like this. You copy and paste those tabs. Do. So, and this is the scenario that we saw earlier, which is that if they interleave exactly like this, what's going to happen is that thread 0 on the left-hand side over here is going to run forward, and because it will hit turn first, and turn over here gets hit second, what's going to happen is when this one tries to run, this check will fail because the step that was done before was turn equals 1. So as a result, thread 0 will pass, which means that it will not forever loop, and it will run through and complete its critical section. And eventually, once it completes its critical section, what's going to happen is it will take the interested array and turn this value to false. As a result, this one will eventually break and gets to come forward. And so it does not matter how you interleave these codes. What ends up happening here is that it will always be the case that only one of these two will succeed. They do this because there's a couple of things that make this work. First of all, every read and write is an atomic action. An atomic action is an action that cannot be interrupted. And that's a concept that we come back to, and we'll come back to a lot. Essentially, it boils down to if you have a line of assembly code that works on shared memory, no other action, no other processor can work on that same section of memory at the same time. This is generally, when you think about assembly code, this is how things work. But as we saw earlier, some things like, for example, the plus equal operator is not an atomic action. You actually have to declare something to make it atomic. Here, this writing a value to your 0, this is an atomic action. A single write or a single read is on every system an atomic action, regardless of however your processor is constructed. And this is true even if you're on a multiprocessor system, that single interested is going to be there. And so what happens is that there's actually only one variable that's shared between them that they both try and write to, and that's the turn variable. And as a result of that, that's really where the race comes in here. We have to have this two-tiered approach because we basically need to say we only really care about the other one at all if it's possibly entering the critical section. If it's not in the critical section at all, then its interested value is going to be false. And if its interested value is true, that means either it's already gone through the critical section, or is going through the critical section right now, in which case it does not matter. It means in which case the second one following absolutely wants to stop. Or it's just about to, which is a scenario we saw here. In this case, we just have to basically arbitrarily choose which one of them goes first. And here, the one we arbitrarily choose is the one that hits the turn variable first, gets to go first. And that makes sense too, because there is a race to make to this turn equals 0 or turn equals 1 line. There's a lot of, the Peterson solution works really nicely for systems that have very, very simple atomic actions. It sucks for any modern system though. This was developed when people first started doing multi-threading, multi-processing, and the result of that multi-threading, multi-processing we didn't really consider the need for atomic actions more than simple reads and writes. And so this was a solution that solved that problem, but it has some real scaling issues. First of all, this only works if you have 2 elements. If you have more than 2 threads, in order to make this work, essentially what you need to do is you need to establish like a bracket tournament where there is a constant hierarchy of which thread will win and which thread will lose. And the code explodes, I want to say quadratically, with the number of threads that could possibly synchronize. Also, it's hard-coded, so essentially you have to establish what is the maximum number of threads that are going to synchronize on this thing beforehand, and once you establish that, it's set. You can't change it without rewriting your code. The other thing, and this is something that we'll get to as well, is that this uses a method of preventing something from going in there that's called a spin lock. And we see that here, where it simply spins forever. Spin locks have a lot of advantages, and we'll talk about those as we go on. But they have one major disadvantage, and that is that they don't, that they just waste processors. And so on a single processor system, if you were interleaving these 2 threads, you end up with a real problem, because whenever thread 1 is being scheduled, whenever it's spinning here, it's doing literally no work. So you'd put it on the CPU and say, all right, go. And then you do no work. In fact, the entire system essentially shuts down while this thread is doing its work. On a multi-core system, the problems aren't quite as bad, and we'll talk about why that is a little bit later. But still, this only works through spin locking, and the lack of atomic actions make it really hard. So what we ended up doing is, in order to get anything more sophisticated, what we have to do is we have to incorporate more complicated approaches into our assembly instructions, and that's where we get to test and set. Test and set is probably the most basic assembly level capability to provide synchronization that we have. The way that test and set works is it performs 2 actions atomically. And so this is actually fairly difficult to engineer. And there's a reason why this wasn't put into CPUs until much later, because simply moving data from a register to another one is that's a single action. But with test and set, it's actually literally performing two different actions. And you have to say, if any other CPU tries to perform these actions on the same data at the same point in time, stop them. And so what test and set does is it will copy a value of a register and then set that register to be 1. And so it does both of these at the same time. The reason why this ends up working so well is that what we can do is when we enter a region, we can take a test and set on our locking register or our locking memory. And so we say, let's do a test and set on there. We will then store that locally into a register, whatever we choose. We then compare the value that we have copied from there to 0. If that value is 0, then what we do is we know that no one else was in the locking beforehand, and we can simply continue forward and execute our critical section. Where we get to the spin lock and the locking aspect of this is that suppose that we had one thread and it locked it beforehand, what would happen is it would read a 0 there, continue forward, and simultaneously change the lock to be 1. So let's copy this critical section and let's go over to our handy dandy pad paper so we can see how they'll interleave with each other. Okay, so I'm going to present this to everyone. Okay, everyone seeing this, the text now? Cool. And it, for some reason, has, no, whatever. All right, so this is the code for entering. And so what will happen here is, let's say that there is an intermingling of code like we had before. We'll space these out. And we'll have to space this one out too. Okay, so we'll have this intermingling, the same thing that we had earlier. And so initially, lock is going to be equal to 0. Register, and this is a global value, so everything has access to the same lock value. Register is local. So each region has their own register and can store it associately. So what test and set will do is simultaneously, this one in here performs 2 actions at the same time. It sets register to be lock's value. So register will be set to 0. And it's going to set lock to be 1. So the important part about this is that test and set register lock from the other thread cannot occur simultaneously with this. It has to occur before or after. One of these two has to occur first. As a result, when we come over here, what's going to happen is, nope. When thread 2 tries to do the same thing, it's going to, again, set register to be lock's value, but this means register is going to be 1. It will also go through and set lock to be 1, but that has no consequence because lock is already 1. So it's like, okay, lock is 1. So now, and that is what the race is for, is who gets to the test and set register lock first. This one will now say, does register equal 0? And this will say the same thing. Here, the answer is yes. Here, the answer is no. So jump if not equal region, what's going to happen here is, does register equal 0? Yes, it does. So it's not going to jump. So it's going to carry on. It's going to return and then eventually go back into the critical section and do whatever work needs to be done there. On the other hand, here, it is going to jump back to enter region. It's going to keep on doing this again. So it's going to come back up to the second thread. It's going to come back to this line, and it's going to try again. It's going to say test and set register lock. It's going to set register to be lock value, but of course, register is still 1 because lock was still 1 because no one's changed it to anything else because test and set always just changes it to 1. So eventually, when thread 0 finishes, what it's going to do is it will go through and actually change lock to be 0. As a result, while thread 2 here is spinning again and again and again and again, eventually one time it's going to get through and it's going to have the value where it's going to read a 0 on there, which is still going to set lock to be 0. Does register 0, does register equal 0? This time it's yes. And now it can finally carry on. So notice how much simpler the code is to do this when you have atomic instructions. When you have this test and set atomic instruction, it makes life really easy because you simply go through the few set of commands, test and set, perform your comparison, and then jump it back. Again, this still has the problem that the other one has, that it's doing a spin lock, but it has a lot of advantages associated with it. The first is it's shorter code, which is nice. The second one is that it's code that's defaultly provided for the specific purpose. Peterson's solution was basically hijacking things that were atomic, but this is actually designed into the architecture itself. There is a question about Peterson's solution, how well it would actually work on a multi-core system. But test and set is designed to work on a multi-core system. In fact, this is the way we build spin locks. When we are building a simple spin lock, this is essentially the assembly code that makes it happen. It still has a disadvantage of spin locks, which is that they spin constantly. As the slide indicates, they're bad because they just waste time. So one option that people realized very quickly was that what we should do was we need to put a thread to sleep. If a thread is spinning, waiting for something to be done, then why should we waste any time with it? Why don't we simply put it to sleep and then wake it up when its resource is available? This is where we get into a concept that's called a semaphore. A semaphore was created by Dijkstra, Edgar Dijkstra, who is a wonderfully brilliant man who is also crazy as all fuck. And we'll talk more about Dijkstra's insanity later on when I'm not exhausted and I believe I'm more entertaining at a later date. But anyways, semaphores are one of the reasons why Dijkstra is a Turing Award winning computer scientist. One fun fact, Dijkstra is probably, aside from Alan Turing, the most important computer scientist that ever lived. He was a professor at UT for many years until he died of lung cancer, but that's what smoking does. Anyways, brilliant man, and he created this concept of semaphores. The semaphores are variable data structures that have a few properties associated with them. The first is that they always keep track of a non-negative integer value. And so they have essentially a member variable. Now, he did this before object-oriented programming was created. So they're not quite that, but that's essentially what they are, is they are an object that has a member variable that's a non-negative integer value. It has two methods, up and down, on it. Up allows you to increase the value, and down allows you to decrease the value. What's going to happen is that if you press up on a semaphore and its value was greater than 1, then there was not really any harm done. Nothing really happened in there. Similarly, if you did it down and the value was greater than 0, then nothing happened in your code. Where things became interesting is when you did down to 0 and up from 0. When you do down on something and its value was greater than 0, so it went down to 0, it would simply decrease the count of the variable. However, if the value of the member variable was already 0 and you try to press down on it, sorry. Sorry. This is what happens when sleep deprived. Anyways, so when you press down on a semaphore that's 0, it's going to go to sleep. Now, it's going to do that in one atomic action. It will say, if you press down, then and it's already 0, then you go to sleep. What will happen is if the semaphore is 0 and someone presses up on it, then what's going to happen is it will wake up another thread. So let's, and at that point, all the downs can try again. So let's go back to our handy dandy paper. And so here, let's start off, and I'm going to create a semaphore. Semaphore S. It's a new semaphore, and we're going right now to say it has a maximum value of 1. Whenever you build a semaphore, you always build it with an associated maximum value. We'll talk about why you'd want to have a semaphore with a non-maximum maximum value other than 1 in a few minutes. But anyways, so we're going to make 2 threads. Thread 1 is just simply going to do its enter critical section. It's simply going to be S down. Its leave critical section is going to be S up. So let's copy and paste and move this over. So both threads are using the same semaphore. If they're not, then it becomes a problem. So what's going to happen here is the value of the semaphore after this line of code is going to change its value from 1 to 0. It's then simply going to continue on with its life. It's going to continue on into its critical section. Wait. Oh, thanks, Kelly. I didn't realize the text was difficult to see here. Let me try making the font bigger. Bloop. Kelly, is that better? I guess it is. Yay. Okay. Okay. So it's going to continue on into its critical section. Over here, on the other hand, what's going to happen here is S is going to go from 0 to 0. This means that S is going to go to sleep. So jealous. Okay, so S is going to go to sleep. So what this means is that it's now going to be blocked, which means it won't be scheduled. And so it is not going to be scheduled and cannot be scheduled until until it is told to wake up. And so it won't wake up until this thread completes. So once this thread presses up, this is the up here is going to, it's actually going to increase the semaphore value from 0 to 1. And it's going to wake up all threads locked on semaphore S. Right now, there's only one thread blocked on semaphore S. We'll talk about what happens when you have multiple threads in a few minutes. But what ends up happening at this point is when this thread now wakes up, now our thread 2 here is going to wake up and then immediately try and reissue its s.down command. Now, you as a developer don't have to worry about reissuing the s.down command. That's essentially what it's doing behind the scenes. But what ends up happening is you don't have to worry about that because it's built into the semaphore, and that'd be madness if you actually ended up worrying about it. But it'll do s.down, and of course, since there's no other, in our example, there's no other thread trying to do a down, it will succeed, and it will go into its critical section. There. It will succeed and go into its critical section. Eventually, once it's done, it'll change the semaphore back to 1. It would wake up anything else, but it happens that nothing else is being woken up. All right. Does anyone have any questions about this? All right. And again, we'll probably I'll refresh this all on Friday as well, because I know this is suboptimal. So I think that I want to make sure that you all fully understand semaphore. So we'll do a brief review on this stuff on Friday. So if you do have any more questions, you can ask about it then. But let's talk about, so let's suppose that we actually had a whole bunch of threads that were using the semaphore at the same time. So we're going to have s.down, 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 s.down. So when all these threads do this, what will end up happening is this thread will succeed, yay, but the rest of these will go to sleep. And so one of the things that ends up happening is eventually this one will wake up. When it wakes up, the other remaining 3 threads, so second, third, and fourth threads all wake up at the same time. In the simplistic implementation of a semaphore, there is no order of those that go. It is a free-for-all. There's advantages to doing this. The biggest advantage is that it's really, really easy to do. You can build that with a test and set, and it's we'll talk more about how to create waiting queues in a bit. But this is the reason why when I said it wakes up when this up command is issued, what's happening is it's changing the semaphore's value from 0 to 1 and waking up all the threads at the same time. Because the semaphore is not, the basic implementation is not in charge of keeping track of which thread is executing. It's simply in charge of saying everything else is not me should be asleep. And so that semaphore, when it does an up there, says, okay, guys, I'm done with it. You can feeding frenzy yourselves and do whatever you need to do to make this happen. And that's exactly what happens. Everyone goes and fights amongst themselves to make this occur. So that is very fast to build, which is the reason why the default implementation does it, but it has some real problems. The biggest problem that we have with that is it creates a scenario called starvation. Starvation is one of the major bad things that occurs in synchronization issues. Starvation is when essentially multiple threads conspire to prevent another thread from succeeding. So consider the following scenario. All 4 of them do down. The first one succeeds. Okay, so it succeeds for whatever reason. After that one finishes, the second thread succeeds. It grabs the lock. It wakes up. It executes its critical section and continues forward. Meanwhile, before the second thread executes its up, we have thread 1 comes back in and does a down. Okay. Now it goes to sleep because thread 2 is currently working. Well, what's going to happen is that thread 2 is eventually going to say, I'm done with my critical section and I need everyone to wake up. All 3 of these threads, thread 1, thread 3, and thread 4, all have thread 1, thread 3, and thread 4 all have equal priority to the semaphore. So it can, and depending on how your implementation of semaphores work, will be the scenario that which thread will win this. Well, maybe you always do it by process ID. Maybe that's how you determine which thread gets to go first. So thread 0 gets to go first. So it succeeds. It wakes up and it goes into its critical section. While it's in its critical section, thread 2 does it down as well. Now, eventually, it does its down, it goes to sleep, and now again, it has equal priority to it. Everyone has the same access to it. So when thread 1 comes along and does its up, anyone can succeed. And in the scenario, let's assume that thread 2 is the one that wins, so it wakes up and it controls the critical section. This scenario where you constantly have 2 threads bouncing back and forth, back and forth, back and forth, back and forth is starvation. And essentially thread 1 and thread 2 are starving the other threads that are here. What's important to note is that starvation is it is a real phenomena. This is not just me bullshitting this up. This is something that you see based off of your semaphores. It occurs because naturally some threads have higher scheduling priority in the OS than other ones, and as a result, OSs tend to favor some threads over other ones. This creates a really bad scenario where threads 3 and 4 never get to execute. So there's a couple solutions for this. One is be more explicit and say that you actually have to be random about what you choose. You can't rely on whims of scheduler. The other one is to maintain a list. Generally, starvation is not deadly. The main thing that happens is not like thread 1 and thread 2 typically are going to conspire forever. That can happen, and that is something that you need to be concerned about if you're using the type of semaphore that doesn't involve maintaining a list of the order that requests were issued. But the main thing that will happen is threads 3 and 4 will be slower because eventually there'll be a break and one of them will win and they'll get to go through. So threads 1 and 2 might conspire for a bit and then stop thread 3. And so starvation is not the end of the world. In practice, however, though, it can be really, really bad. And the problem with starvation is that it appears like the world is working. If you were to have a monitor on this and it was watching the threads that were executing, you would simply see thread 3 and 4 in practice just behave slower. And so you'd have to wonder, why are they slowing down so much? What is going on here? And that becomes a very difficult thing to track down. Not impossible, but a much more difficult thing that you have to delicately track down. And that's where a lot of the problems with multiprocessor scheduling comes in, is that you have to be very clever about how you write your code. Otherwise, you run a real risk of making problems that are very difficult to track down at runtime or track down through code examinations later. And starvation is the first of those, and it can be really bad, but it is sort of like one of the deadly sins of multiprocessor scheduling, and we'll talk more about that later. There's one last thing. Let's talk about one more thing before we end up breaking for the day. I mentioned that semaphores have a maximum value. And if you are using a semaphore simply to protect a critical section, it's called a mutex. But semaphores have a much wider range of capabilities than that. They can be used to protect larger entities. And this is an example that we're not going to be able to get through today because it's going to absolutely require me to draw on the board with this. But the idea here is that if we think about, if we consider the example of streaming video, each of you have a buffer on your computer, right? We've all seen the buffering thing. We've all seen that work. But the question is, how do systems detect the amount of things on the buffer? And so essentially the way that video works is you're essentially putting a lot of frames, individual videos onto a queue. And that queue will always pull off the first in, first out ordering. The buffer is another name for a queue. So it puts things at the end of the queue. Whenever you're downloading something from the end of the queue. And whenever you're watching a video, you're moving something from the front of the queue. And that's the whole point of a buffer. But the thing is that if you're watching video and you have not downloaded any frames, then your video player should actually go to sleep. It should not try and draw data from a dry well. Similarly, if your network card is looking at a buffer that's completely full, it should stop receiving data. It should say, okay, hold on for a second. I've got too much data here. The video player is not pulling it off at the correct rate. I need to stop putting data on here. Otherwise, I'm going to overwhelm the buffer. And that's essentially how you can use a semaphore that's a value above 1. You place a semaphore over a priority queue, over a queue or buffer, and you set it to be the number of elements. Essentially, every time an element is removed, you have a semaphore that says every time when the consumer, the video player, should go to sleep when there's nothing in the queue. And so when the number of elements in the queue has gone to 0, then you put the video player to sleep. Similarly, and you have another semaphore that it has the size of the buffer on it. And whenever you want to add an element onto it, if it's already full, then the network card should go to sleep and it should wake up later when elements have been removed from the queue. And so at a high level, that's how we can use semaphores to produce these type of results. We can use semaphores to keep track of elements that contain more than one value. So we'll talk more about this on Friday. I'm really sorry I was not able to be there in class today. I know we're missing a lot of class because of the high holidays, and I felt really bad that I couldn't get one more in, which is why I wanted to do the video, because I felt like I was letting y'all down by not being there for this. But I think we covered a lot of introductory stuff on this stuff, and we can review some of the more complicated topics on Friday, and then hopefully we won't have any more distractions from this until the end of the semester. Anyways, again, really sorry about this. I'm grading your tests now. Maybe I'll have them by Friday. We'll see. Again, intros work comes first because they need their answers a lot more than y'all. So if you have any questions, I'll be there tomorrow. Yeah, my normal office hours tomorrow. And but again, no class on Wednesday. All right. Well, again, thanks you all for showing up. I really appreciate it. Thanks, Kelly, and everyone else who's in the classroom. I really appreciate you all setting up that video and watching it there. And yeah, I'll see you all later. Have fun.